In this lecture, we're talking about Eulerian closed chains and Hamiltonian passer cycles. So first we need some terminology. A degree for each vertex is the number of edges incident to that vertex. So for example, this vertex in this graph, we've got 3 edges coming out of it. So that has degree 3. You can pretty easily count the other ones. This one has degree 2. This one has degree 3. And this one has degree 2. An Eulerian closed chain is a cycle that traverses each edge exactly once. So we have to start and end in the same place, and we have to go along each edge exactly once. What are the uses of that? Well, in real life, we might want to clear the roads of snow. Probably only twice a year in Seattle, but in other places we would do it more. You might also be playing the game Pac-Man. You've got to eat all the stuff along every path. You don't end up doing an Eulerian closed chain because you got to run from ghosts, but that would be the easiest way to do it if you could. And it turns out this problem, so the problem is, does there exist an Eulerian closed chain for a graph? And that problem is easy. There's a theorem from 1736. If you've got combinatorics and graph theory theorem from that early, it's an easy problem. And the theorem says a multigraph G, multigraph meaning there can be multiple edges between any pair of vertices. Multigraph has an Eulerian closed chain if and only if it is connected. We don't want a piece of graph here and then another piece over here. You're never going to be able to get to it. Up to isolated vertices, meaning it doesn't have to be completely connected. If I put like one vertex over there, that doesn't affect anything because in Eulerian closed chains, we only care about traversing each edge. Okay, connected up to isolated vertices, and every vertex has even degree. Let's think about why we need that. Well, if you start at a vertex with odd degree and you leave, you're gonna have to come back eventually. But if it has odd degree, you're not going to leave and come back the same number of times. So there's no way we can finish the cycle. And it doesn't matter if I don't start there. If I get to this vertex eventually, it has odd degree, same thing. I'm going to leave and come back a different number of times. So that's not okay. So in this graph, if I tried to make an Eulerian closed chain, let's say I start from here, go here, 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 and here, I'm now not ending the same place I started. I can fix this. This is a multigraph, so I can fix it. If I just add that edge, that's a multigraph. Edges don't have to be drawn straight. If I can draw straight, often I do. Now every edge has even degree, so the theorem says there has to exist an Eulerian closed chain. Well, of course there does. The one I drew almost works. Go here, 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 and then this edge helps me get back to where I started. That's the Eulerian closed chain for that graph. It's a famous problem called the Bridges of Knigsberg, introduced also by Euler. And the story is he was standing here. So this is a real place in Germany. There's a little island here, there's land over here, and there's these riverish things going here, and there's 7 bridges. 1, 2, 3, 4, 5, 6, 7. And he's standing on, I don't know if he's on the island or somewhere, and he's thinking, could I cross each bridge exactly once? It's not quite looking for an Eulerian closed chain because he doesn't require that we start and end in the same place, but it's pretty close. And it's pretty hard to see just by looking this way if that exists. But we can turn this into a graph theory problem. Okay, so every piece of land is going to be a vertex, and every bridge is going to be an edge. So here's the island, and then that shore is a vertex, this shore is a vertex, and this little peninsula thing is a vertex. And then I just draw an edge for every bridge. So there's 2 bridges going there. So there's 2 bridges. There's a bridge going from the island to the peninsula. There's 2 bridges going here. And then these 2 bridges from each shore to the peninsula. Okay, and let's look at the degree. So this vertex has degree 1, 2, 3, 4, 5. This vertex has degree 3, and degree 3. And we can't quite use Euler's theorem because we're not looking for an Eulerian closed chain, but we can modify it. So if we're allowed to start and end in different places, then that says 2 of the vertices can have odd degree. Remember, before we added this edge on this one, 2 of the vertices had odd degree. I could traverse each edge exactly once, I just didn't start and end in the same place. If more than 2 have odd degree, I'm going to have a problem, because the ones that I don't start and end at, I do have to come into and leave the same number of times. Well, look at this one. Every vertex has odd degree. There are 4 vertices with odd degree. There's no way I can make even an Eulerian path, is what this would be called, not a closed chain. It doesn't have to be a cycle. Can't do it. Okay, so that's the solution to the Bridges of Knigsberg problem. I cannot cross each bridge exactly once. Hamiltonian paths and cycles are different. So Eulerian closed chains, I wanted to cross each edge once. A Hamiltonian path or cycle visits each vertex exactly once. What might we use this for? Well, I don't care what roads I'm going along, but maybe I'm picking up supplies. Then I just need to make sure I visit the supply stations once. And it turns out this problem is very hard. Eulerian closed chain problem was easy, solved almost 3 centuries ago. This problem is hard, it's not yet solved. In fact, it's NP complete. Meaning it's on that long list of problems that are not quite solved, and each one could solve every other one, and if you solve it, then you become famous. There are some things that we know do have Hamiltonian cycles. So examples, definitely a cycle graph, meaning a graph that's just a cycle. Well, of course, if the graph is just one cycle, it's very easy to find a Hamiltonian cycle. Complete graph. Complete graph means I draw in as many edges as possible. So let's do it for 4 vertices. Every pair of vertices that can be connected, so not a multigraph, but just a regular graph. Everything that can be connected is. And of course, a complete graph contains a cycle graph. So that certainly has a Hamiltonian cycle. And a cool one is any graph for a Platonic solid has a Hamiltonian cycle. Platonic solids are those 5 solids that have all the same faces. So tetrahedron, cube, octahedron, dodecahedron, and icosahedron. Pretty well studied in early geometry. So let's just do an example here. This is the graph for a cube. It's like if you're looking at a cube from the top view, and then just every vertex of the cube is a vertex, and every edge is an edge. We don't worry about faces. Okay, let's just find our Hamiltonian cycle on this one. Maybe I start from this vertex. I'll just go almost all the way around the inner cube, then I walk to the outer cube, and I can walk along there, and then come back to my original. There's my Hamiltonian cycle on that graph.